So now we have gone through the whole, all the different parts of our optical spectroscopy setup and discussed different things which are used and some of their properties. And now for all of this, the spectral resolution instruments we looked at, like the prism and the grating, they all changed so that different colors came out in different directions. And now we're going to back up and look at some spectrally resolving instruments which can resolve this, but they do it in a different way, so it's not in different direction necessarily. And the first one we're going to look at is a so-called Fourier transform spectrometer. So in a principal Fourier transform spectrometer, the light comes in from out here, and then you have a beam splitter splitting it up so that the light can travel two different paths. It can travel this path straight 1, which has a length S1, or it can travel this path here, which is longer, which has a path S2. And we'll just call, and then they hit a beam splitter over here, both of them, and that then they are, the transmission of the first beam goes out in this direction and the reflection of a second beam goes out in this direction. So that means over here you will have an interference of the two light beams. And the length difference between the two arms, we can call this delta S. And if we look at the relative phase between these two, the phase difference between the two light fields, then this is given by 2 pi over lambda times delta S. This gives the phase difference. Or I would rather write it as delta S over lambda times 2 pi. This gives you the phase difference between the two. So this will of course repeat every time delta S becomes 1 lambda larger, your phase will just go back to the same place again. Well, I mean the phase here will grow, but since you can't see a difference in a phase, or if it's an altitude of 360 degrees, it will repeat. So how can you use this for a spectral resolution instrument? So if we now take this second path here and we move these two mirrors, this mirror here and this mirror here up, then we are moving delta S here. And when we do this, depending on what frequency we have coming in, we can get either constructive interference or destructive interference in this arm over here. And when the two beams coming out here has the same relative phase, then they interfere constructively and we get a large intensity. If we then move this back so that the phase of them differ by 180 degrees or pi, then they are interfering destructively. Then if we move it back further, then they will again, when it's 2 pi difference, then they will again interfere constructively, and so on. And that means that when the relative difference between these two paths, the first time this happens, is half a lambda, then that's the same thing as having a pi difference, phase difference, then we get destructive interference. When it's lambda, we get constructive interference. When it's 3 over 2 lambda, we get destructive interference, and so on. So if we now move these far, we can get a pattern like this for a single light field. And that means that the oscillation frequency of this pattern, compared to how far we have moved these back, will tell us what frequency our light source had. So if we have a different, because this depends of course on lambda, so if we had a different wavelength or a different frequency of a light source, this pattern would look differently. Now in principle, when they make these spectrometers, they look, in practice, they look a little bit different because this is more stable. We have a light source coming in and a single beam splitter. And now the light here is split up, going up to this mirror here, and then comes back and goes out this way. Part of it goes out this way. And the transmitted beam for this beam splitter goes over, hits this mirror here, and comes back, and then it goes down here. And then we move one of these mirrors back. So this is easier than moving two mirrors and not introducing any disturbance. And this is of course a Michelson, or of course this geometry is called a Michelson interferometer. So just like in our previous graph, if we have a single frequency coming in, we'll get a sinusoid pattern like this. But if we instead, for example, have two discrete frequencies coming in, omega 1 and omega 2, then we'll get a pattern like this. And if we take the Fourier transform of this pattern up here, we'll get a single frequency. If we take a Fourier transform of this recorded pattern here, we will get two discrete frequencies. And then we'll have to put in the conversion factor to actually get it into wavelength. So this was for one frequency and many frequencies. But if we have, one frequency and two frequencies. If we have many frequencies, we will get some pattern like this, some strange interference pattern like this. And by doing the same thing with this interference pattern, taking the Fourier transform of it, we can get the spectral content of a light which was impinging. So we have a single point detector and we measure it as we move a mirror back. We measure this pattern and we get the content, the wavelength content of our incoming signal. But it's fairly difficult to do this well. You have to have very good control of how far back you have moved the detector. And you could of course move it back with an equal speed, but it's very difficult to move it back exactly the same amount the same time. So therefore they have come up with a small trick for these spectrometers where they build two different of them using the same middle mirror. So over here we have a reference Michelson interferometer. And over here we have a interferometer which we actually want to measure. So if we start with this one, we have two different incoming light sources into this interferometer. So if you see, here's a beam splitter, here's one mirror, and here's the other mirror of this interferometer. In the other side, the radiation comes in from here. Here's the beam splitter, here's one mirror, and here is the other mirror of this interferometer. And the important thing here is that this mirror is the same mirror for both interferometers. So if we now move to the left reference interferometer over here, what we have is we have an incoming single frequency laser, single wavelength laser, and that goes through the interferometer and hits the detector 2 here. And then we have a continuous spectrum, so something like, for example, a light bulb, which has a very, very broad spectrum, which comes in and goes to the detector 2. And the helium laser, since it's a very coherent source, it will give a pattern like this, which can be used as a reference for how far we have moved for this other when we want to analyze over here. So why do we have a broad spectrum? Well, we also want to know when are we at the 0 point. So when are these two paths in this one here exactly the same length? And here, since we have such a broad spectrum for something like a light bulb, then we will only get a single peak in the middle when they interfere, when it's exactly the same length. Everywhere else we will get no interference pattern. And then in the second arm over here, we get the interference pattern which we analyze to find out what content the light source over here had. And here is a picture of a Fourier transform spectrometer. And they can of course look very differently. This is an instrument used in chemical analysis, I think. But as we saw here, I mean, here we had two different paths going through the interferometer, but you can actually also make it with many different paths. So you can make these Fourier transform spectrometers into spectrally resolving instruments. So that when you start off with something you want to image, and you have light coming from each and every point inside this image. And each of these light paths traces separately through your Fourier transform spectrometer. And then you have then you are down here, instead of having a single point detector or two detectors, you have an array of detectors, so a camera. And then you quickly store all the images from this camera, and in each pixel you will get one of these shapes like what it looks like here. I mean, you will get one of these traces in each pixel. And then you can Fourier transform all of these pixels separately, and that means that you get a full spectrum in each pixel of your image. So this is a kind of instrument which allows you not only to take like a normal camera 3 colors, but it actually allows you to get a full spectrum in each pixel. The downside is, of course, that you have to move this mirror back, so that will take some time. So you have to collect light over some time. So the frame rate will be fairly low. And here is an example picture where they have done this, and they have looked for chemical release from these chimneys here, and then they have false coded the spectrum of these chemicals into this flame coming out here. So you can see here that something is emitting from outside from this chimney. And NH3 is ammonia, so I guess that they were looking for ammonia in this case. And here is another example. This is so-called hyperspectral image, where you have put this in a plane or a satellite, and then you take a photo of Earth with all the different spectral components. And by, for example, looking at the spectrum for chlorophyll, you can see how much chlorophyll there is in a forest, and you can also use it for things like looking for other pollutants which has a strong spectral feature. Now I would like to talk about a cousin of a Fourier transform spectrometer, which is called a Fabry-Perot spectrometer. But let us first quickly look on a Fabry-Perot interferometer. So we have two mirrors. In this case it's a solid substrate, but it doesn't have to be. We have two mirrors separated by some distance d. And now we have drawn it with the light coming in with a bit of an angle, but this is so it's easier to see. Sometimes Fabry-Perot interferometer is really used like this, but for the Fabry-Perot spectrometer it actually comes in straight most of the time. So what happens here is that the light, some of the light is reflected in the first surface, some of the light leaks in, is reflected back, and then it leaks out here, and then it's reflected, and then it leaks out here. And all of these different light fields, they interfere constructively, and the difference in how long they have traveled is how far the beam have traveled as going through the Fabry-Perot interferometer. So that means that you get regular interference fringes from one of these Fabry-Perot interferometers. So here we see a transmission through a Fabry-Perot interferometer. Depending on the reflectivity, if we have very low reflectivity, it goes up and down as you change the length of a Fabry-Perot interferometer. In a similar way as we changed the length before. And when we increase the reflectivity, that means that the light who gets coupled into the cavity stays inside the cavity much longer, and we can compare light which was introduced to the cavity much earlier to light which are introduced at a later point. And these peaks become more and more narrow until they can become very, very narrow. How the distance between the peaks compared to how wide the peaks are is called the finesse of the Fabry-Perot cavity. Okay, so if we now compare, if we have a single frequency, so here we have a single frequency impinging on a Michelson interferometer, so on a Fourier transform spectrometer. And if we change the position of this mirror over here, we get a sinusoidally changing pattern like this. And when we take the Fourier transform, we get a single peak. And now we have two mirrors instead. The light is impinging. We change the distance between these two mirrors, between this position and this position. And then we look over here, and now we get these peaks when we are in resonance with, when the light coming in is in resonance with our cavity. We take the Fourier transform of this, and we get some shape like this. And from this you can back out what the color was, what the wavelength was for the light which impinged on. Of course, if we have multiple sources, I mean a broadband source coming in on a Michelson interferometer, as we talked before, if we take the Fourier transform, we simply get the spectrum scaled. And if we have a Fabry-Perot spectrometer, when we take the Fourier transform, what we get needs a little bit more work to back out what spectrum we had. So this means that the Fabry-Perot spectrometer needs more computation before you get the result compared to a Fourier transform spectrometer. But the benefits of a Fabry-Perot interferometer is that it's only two surfaces, so which are supposed to be moved in respect to each other. So that means that it's easier to make these kind of spectrometers stable. It's a much easier geometry, and therefore they have lately become much more popular. Okay, so that was the last of a spectrally resolving instrument. So now I'm going to talk just a little bit about some of the components, some of these optical components, and some of the properties of these. So here we have lenses and mirrors, and between redirecting the light. So we'll look at these components. So mirrors can of course be made out of with different metals, and here we have aluminium, silver and gold, and the reflectivity for the different materials. And as you for example can see, gold, when you come up above something like 800 nanometer, the gold mirrors are fairly good. They're not super good, but they're fairly good. But in visible range they're not so good. But if you need better mirrors than this, so how do you go about it? So what you do then is that you create so-called dielectric mirrors. And what this is stacks of material, thin layers, typically a few hundred nanometers thick, depending on the wavelength, where you have thin layers of slightly higher index of refraction, slightly lower index of refraction, slightly higher, and so on. And these are all dielectric. They're not metal, so they're not conducting. And that's why I call a dielectric mirror. And when the light impinges in on this, you get a little bit of light which is reflected from the first surface, and then you get a little bit of light reflected on the second surface here between these two index of refraction, and from the next surface, and so on and so forth. And for some wavelength where all of these different reflection interfere constructively, you can get very, very high reflectivity. And here we have some examples of dielectric mirrors. So if you want to have tailor the performance of your mirror, you have to have several layers. So you can see here, if you have one pair, you start off with very low reflectivity, and then as you go up and have 15 pairs, you can see that you have very high reflectivity over a broad wavelength range. And you can not only make mirrors with this technology, you can also make dielectric interference filters. So you can make these in a way so that only some wavelength of the light are transmitted through them and the other wavelengths are reflected. And then you can use either the reflection or the transmission. And you can make things like very narrow bandpass filter, which only lets through or reflects a single frequency, or high pass filter or low pass filter, or more exotic kind of filters for optical light. And these kind of structures are not only used in these filters and mirrors, but actually some reflection from some animals comes from these from thin film structures. So for example, the peacock here, these very, very bright colors in its feathers comes from thin layers where you have these sort of interference filters. So this is different from if you have paint. The paint is based on that the atoms inside this paint absorb, like we talked about earlier, absorb some of the colors impinging, and only the rest of the colors are reflected off that material. While here it's thin layers, so it's the mechanical, how wide, thick these layers are, which designs the color which they have. Another application of these kind of structures is for so-called fiber Bragg ratings. And these are made in a fairly interesting way. What you do is you take a fiber and you make it so that you only have a center of a fiber visible. So this is an optical fiber where the light is trapped inside the core of the fiber. And then you take two ultraviolet beams and you cross them inside the fiber. And that means since you have two beams which are phase locks to each other, you get a standing pattern inside here. So you have high intensity, low intensity, high intensity, low intensity, and so on. And these UV beams, they permanently change the index of refraction of a glass slightly, very slightly, but enough that you have created a structure similar to the structure which we saw over here. And that means that inside the fiber, if a light comes traveling inside the fiber, some colors can be reflected and some colors can be transmitted, and you can make mirrors. And by doing this at multiple different places inside the fiber, you can also create fiber cavities. So by putting one mirror here and one mirror over here, you create a fiber cavity. And I would also like to say that these mirrors, they can have a reflectivity which is as high as 99.999%, so very, very high reflectivity. And one example where this is used is for laser stabilization, where you place one mirror on one side over here and one mirror over here. And then you measure the distance between these two mirrors. You have formed a fabric row cavity between these two mirrors, and you measure the distance between these two mirrors very precisely. And in our lab, which I work, we have a laser which is stabilized to such a cavity, and the precision of how long this cavity are on with short timescales, like a second, is less than the radius of a proton. So you can actually do this. There are a lot more to it. I have some more discussion of how to do that here, but if anybody is interested, you can come and ask me and I will tell you more about it. You can also do the opposite to highly reflecting coatings, which is namely anti-reflection coating. And again, here it depends on if you have many layers, you can tailor your anti-reflection coating to have more desired properties according to what you would like. So here's a single one layer, and then there's a two layer, and then there's a three layer, and you see how it becomes broader. And the more layer you add, the lower reflectivity you can get over a wider wavelength range, for example. And again, you can get very, very good performance. You can get much below 1% reflectivity. I think the best I've seen is 0.01% reflectivity from such an anti-reflection coating. So we have looked at different kinds of spectroscopy where we have a light source, we go through a sample, some light go missing, we divide it up in different directions, and we look at what are the spectral components which was absorbed in this sample. But there is also, you can also do other kind of spectroscopy. So for example, you can do spectroscopy where you have a spectrally emitting sample. So this sample which you want to analyze emits light by itself. An example of that is a flame. And here you can of course either look at the flame itself, but what normally is done is that you introduce some sort of atoms, typically in a solution, which burns inside the flame and are then excited by the flame, and then you look at the emission from these atoms which has been introduced. Another example is where you want to investigate a metal, and you use an electrode to create a spark from this metal, and this emits light, and then you analyze the light from this. Another kind of spectroscopy is, and now I have moved the light to show it a little more careful. I mean, it doesn't necessarily have to see it from the side. Is fluorescent spectroscopy, and in this case, you take a light source which is not so broad, but which you shine in, and often you do it from the side like this, because that means the light continuing out here goes in this direction, so not so much light is scattered in the sideways direction. And then you have a emission excitation filter, which means that you excite somewhere, and then here you have a detection filter which takes away the light which came in from here. And then you can only look at the fluorescence coming out from the sample. And again, you can use a spectrally resolving instrument to look at what different fluorescence came out. And we have already talked about how the fluorescence work. And again, you get this shift. You excite it in one place over here, and then you get a shift, and then you have a fluorescence coming out at a different wavelength. And yeah, these are optical filters for the excitation and the detection. So if we look in our diagram over here, then the excitation filter, that will have a transmission like this, and then the emission filter, that will have a transmission something like that. So that means we excite over here, and then we look at the transmission. So this emission filter blocks this excitation light, and you can only see the fluorescence coming out. Another way of doing fluorescent spectroscopy is to have a monochromator, which is again a spectrally resolving instrument with a slit on the output, selecting a single wavelength, and then you have a filter on the output most of the time to suppress this excitation light which went through the monochromator, and then you can look at the fluorescent at different wavelengths. Okay, so that was the end of the optical spectroscopy lecture, and the next lecture will be about laser spectroscopy. So this which comes out in one go now normally corresponds to roughly 2 lectures, and the laser spectroscopy normally corresponds to roughly 1 lecture. So the laser spectroscopy will be considerably shorter than this one. Okay, bye bye.